Alright, good evening, students. Welcome again to CTS physics class on Tuesday evening. Actually, today was supposed to be our last day. However, we have a makeup session on Friday coming. This Friday, not sure the time, but we'll inform you about the time mm, as the week go by. So we're gonna complete the specimen 2020, the paper 41, and then we're gonna do a paper 61. Those are 2020 specimen, which was supposed to be for this year. So it's kind of like a guide of how the exam going to be. Last week we stopped off on question 9 of paper 2 or paper 41 if you want to see. The question here says in number 9, a plastic rod is rubbed with a cloth and becomes positively charged. After charging, the rod is held close to the suspended tennis ball. The table tennis ball is covered with metal paint and is uncharged. Describe what happens to the charges in a metal paint. So the charges in a metal paint on the ball as the positively charged rod is brought close to it. So this is positives here. These are all positively charged. So this here is positively charged. This rod itself is positively charged. Good. And we are saying here um, that describe what happens describe what happens right describe what happens to the metal paint on the ball on the positively charged rod as it brought close to the ball. So you remember the ball here, we go back to the question. They say plastic rod is rubbed with a cloth and becomes positively charged. After charging, the rod is held close to the suspended ball. So all of these are plus. The positive part going to attract obviously the electrons, so the negative charges. So what is going to happen is because the tennis ball is covered with paint and is uncharged, the negative charges of the rod moves towards the rod. Good. So this side here we go over. A plastic rod is rubbed with a cloth and becomes positively charged. After charging, the rod is held close to the suspended tennis ball, shown in figure 9.1. The table tennis ball is covered with metal paint and is uncharged. Good. So they're asking, describe what happens to the charges in the metal paint on the ball as the positively charged rod is brought close to it. The negative charges the negative charges on the metal pinball uh, charges in the metal paintball will move towards will move towards the rod or towards the right again towards the rod. So we go back. So what's going to happen here, basically all the minus signs in the ball going to come to the edge here to attract this positive in the rod. All the positives in your rod, you're going to move towards it to attract it. Good. So because negative, because of the law of electrostatics, we say that the opposite charges attract each other. The positive charges would go towards the negative charge will move towards the positive charges. Good. So it would move towards it, and then you'll get a force of attraction here. Good, towards the positive charge. So the negative charges in the metal paintball will move towards the rod. Good, everybody okay with that so far? Nice. Moving on. They say the ball is attracted towards the charge rod. Explain why this happens given that the ball is uncharged. Remember, I just talked about it because of the charges, they tend to attract each other. Good. I was just saying that same exact thing. That because due to opposite, due to the right, due to the law of electrostatics, comma, the opposite charges will attract each other, right? So they will attract because will attract each other, hence will attract each other, hence negative charges moves towards positive charges on rod, right? So that's a force attraction. Is everybody okay with that one so far? Nice. Good. They say what is the state the unit in which electric charge is measured? Q is equal to I by T, where Q is in coulombs. And we call that capital C is for coulombs, right? And your formula for that would have been Q is equals to I multiplied by T, where I is current and your current is in seconds. In amps, sorry, your time is T is in seconds and your Q is in coulombs, which is in capital C. In so that's the formula that we would have used as well. So Q is equal to I by T. That's the formula we use in electrostatics. Everybody okay with question 9? Nice. Moving on now. Good. Number 10. Number 10 here says emissions of a radioactive source passes through a hole in a LED screen. There's this hole here, right? Into a magnetic field. The experiment is carried out in a vacuum. Good. They say radiation detectors are placed between A, B, and C. This it gives the following readings: 543, 396, and 32. They actually the radioactive source is then completely removed. You get counts of 33 at point A, counts at 30 at point B, and counts of 31 at point C. From the given data, given for position A, B, and C, deduce the type of emission coming from the radioactive source. Explain your reasoning. So I'm going back to our notes, which we would have done, which is radioactivity. Right, and we talk about a magnetic field. This is our magnetic field here. So one would be point A, B, and point C. So we have alpha, beta, and gamma. So they are asking a question here, right? They are asking a question here in the paper. Deduce deduce from this type of mission comment and explain your reasoning. So at position A, so at position A, which you think it is? At position A, what particles we have? Position A. We go back to position A. Position A looks like this here. From our diagram that we would have drawn as well. Position A should be good, alpha, nice, excellent. So position A is alpha. So position A, they are alpha particles. Wait. At position A, right, it said explain your reason. At position, all right, first let me start at position B. So at position B, we have the gamma particles, they are gamma rays. Why they are gamma rays? Because it is not affected by gamma rays. Since particles, since it is not deflected, by the magnetic field. Remember gamma rays again, if we go back, gamma rays are not are the the rays that are not affected by electric field or magnetic field. Good. So that is position B. Let's go. At position C. At position C, there is what? We call that beta. There is beta particles. Why we consider it to be beta particles? Because it is deflected. Right? Because it is deflected out of the page through which can out of the page noted from the left hand rule. Good. I remember was the left hand rule from left hand rule, right? And at position A, now what I wanted to notice between position A, B and C, if a B had a higher amount going through the magnetic field and slide, then position A, there is very low cost but increased by 1, which means that there isn't any alpha particles. Okay? So at position A, there is no alpha particles, or there is no alpha particles, or we can say there is only background radiation. Why we say background radiation is because you went from 32 to 33. If it had alpha particles, it would have been far higher. It wouldn't have been 32, it would be much more than that. Alright, so it isn't alpha particles. However, B and C, B is gamma, C is beta, and A, just through there's only background radiation at A. But remember, there's no alpha particle. If it was alpha particles, then this value would have been much higher. 32 would have been much higher. Good. Take down that side and we're moving on. Right, so everybody okay with this part here, especially IGC people? Nice. So moving forward, light speed ahead. All right, so number 11, they said in number 11 here, in Geiger and Mazen's alpha particle scattered experiment, alpha particles were directed at a very thin gold foil, which is shown here. They said figure 11.1 shows 5 of the nuclei, which is these 5 black dots here, in one layer in a gold foil. Also shown are parts of 3 alpha particles in a gold directed at the foil. On figure 11.1, complete the paths of the alpha particles passing through the gold coil. Right, so your particles would look like this. So the first one, they said to complete the path. So this one will go straight across, right? Well, I'm gonna straighten up that. So if this one will go straight across, this one here will go towards the top one would go towards the would be deflected something like this. So wait, I'm gonna draw this properly. Alright, so it'll be deflected something like this. Alright, and this one here will be deflected like this. So sorry, this should have been so. Should have been like this, so it should have been, well, it should be kind of curved like that. Alright, so those are the how it's going to look. So this is what this supposed to look like. Something similar. This should have be a little more curvy, I guess. Straight like that. Good. So you deflect to the top, deflect to the bottom, and right back to the left. Deflect to the right. This one goes straight. That's because it's in between. Good. So those are your particle. How it's supposed to have been in your thing. So they had asked the question, I cleared these drawings. Asking this the question here lower down. They said, state the result of the experiment that shows that an atom consists of a very tiny charged core of a charged core containing almost all the mass of the atom. State the result of the experiment that shows that an atom consists of a very tiny charged core containing almost all the mass of the atom. This is seen through the through the deflection of the bottom ray being no this is seen through the deflection of of more than seen through a deflection greater than 90 degrees 90 degrees by the bottom particle. Alright. This is state the sign of the charge on its core. What is the charge of an alpha particle? It is positive. The alpha particle is positive. If you remember, it's 4,2. So it is a positive. That's the charges is positive, and state what occupies the space between these charge core. What occupies the space between the charge core? The positive sign. If it's you should have positive 2, but they're not considering with the figures, they're actually about the sign, which is a positive. Alpha is positive. So this is state what is between these charge cores, and we could say what is between these charge cores. Most of the time it be electrons or vacuum of space, right? So we can say electrons, right? The nuclide notation of a particle, alpha particle, is 4,2, which means that it's positive 2, as was explained. State the number of protons and neutrons in an alpha particle. Protons is the bottom number. We have 2 protons. Neutrons, top minus bottom, is going to be 4 minus 2. Your answer is 2. Good. So that's how we get the protons and the neutrons. Everyone okay with this so far? Especially IGCSE students. Good. So I'm going to move on now to this paper, which is a paper 61 for things. So today we just focus on IGC. We have a makeup class Friday, which I'll focus on the last thing, which is both IGC and CXC. However, just focusing on the IGC right now in today's class. Good. So we're going to do a paper 61. So can I take off this? Nice. So moving on here. I hope everybody taking all the answers because I'd already saved these answers here. Alright, so that answers the question, So this is 20. This is a specimen paper for this year for you guys and all. So hopefully we should be able to complete this here as well. So the question here says in the specimen paper, I think I had posted it on your WhatsApp group chat. I could add it here as well, just in case. Right, so I'm going to add the file for you all. No. right? So that's what we're going to work on now. Right, so here the question here says, everybody see the paper, especially IGC students? Right, here the question says in 2020, this is a paper 61 or paper 3. A student is determining the mass of a load using a balancing method. So what they do, they have a pivot, is like a seesaw in essence. They put a load at this point and they would put a certain mass at this point and adjust it in order for the beam to balance. They said figure 1.1 shows the apparatus. The load X has been taped to the metal ruler, which is here, so that its center is exactly over the 90 centimeter mark. Alright, it is not moved during the experiment. A mass of 40 gram is placed on the ruler and its position is adjusted so that the ruler is near as possible to being balanced, with the 50 centimeter mark being exactly over the pivot. Figure 1.2 shows part of the rule when it is balanced. The procedure is repeated for a range of masses as shown between B, C, D, and E when balanced with 50, 60, 70, and 80. They are asking the question here, which is all of those here. They are asking you in part A of the question, part 1, figure 1.2, to determine D. So we need to follow this table here between the mass of the pivot and the balance for each value of record. Now mind you, 50 here is this part here. It's wrong. So, right. This part here is where the is where the pivot is placed. That's here. Right. So that's this point here. This mass is where it is positioned here. Good. Forget the next piece. We need consumer. So this here is the distance D, and this is your mass M. Right, which is this whole thing here is M, and this is the distance between this point and your M. They are asking here to follow out for each of the table. So here is 50, here's 25, here's 30, here's 35, 40. So all of that is what they give us. So what we're going to do here, we're going to try as best as possible to find out the actual measurements. So, right, so between here to here. So right now as is here, as is here is the pivot. So that's 50. Here is 25. So that means this position, which is half the amount, we always have to check half, right? Because that's where the center of the mass is. Right, so that's half. So, wrong. Right. So this here is half, which is, if here is 25, then here going to be between here to here is 30. This bold line is the line that we just marked, and the bold line is where 20 supposed to be. So here should have been 20. Good. So if here is 20, so if here is 20, if this point is 20, then the distance between here uh, distance between here to here is what? If here is 50 and here is 20, 20 is going to be 50 minus 20. Your distance is actually how much? 30 centimeter. That's the first value we had to calculate. So we get 30. So the first one is 30. Everybody understand how we get a 30? We take the center, which is 50, and we minus it from where the center of the mass was, which is at 20. So your first one is 30 centimeters. Second one, so that's your first one. I'm going to put in your value here. So first one, we get 30, right? 30 centimeters. Right. They are asking later down in the table 1 over d. So 1 over 30 is how much? 1 divided by 30 when we calculate it. 1 divided by 30, I get 0.003. Good? We're going at the 50 mark now. We're going at the 50 mark here. So at the 50 mark, that is enlarging it so you can see hopefully. Alright, so for the 50 mark here, watch here. Here is at this point. So your 50 mark is here. Right, so between here to here, you're going to be 50 minus what value is this? So if here to here is 25, this is going to be 26, this is going to be 27, this is going to be 28, here going to be 29, and this is 30. So each of these bone lines is 1. So we need to find the center. The center of the bob would be here. The center of the bob is actually at this position here. Which is, if we notice, a stroke before this value. So watch here was 25 and here was 26. This next line, sorry, not this next one, this next bold line here is 26. Good, so that means there's one increment before the 26. So if here is 25, then here going to be 25.2, 25.4, 25.6, 25.8. So your answer is 25.8. 25.8, right? So it's going to be 50 minus 25.8. How much I get? 50 minus 25.8, you get 24.2 centimeters, because the distance between here and the 50 mark. Right, so your second one here, we're going down. The second one is 24.2, we just got. Alright, and so it'll be 1 divided by 24.2. 1 divided by, how we get the 1? We're using this equation, 1 over d. So it's going to be 1 over, what was it, the value? 24.2, which is 0.04. Right? Moving on again, we're going to the 61 now. We're going to 60 thing. So we're going to draw a line from the center for the 60, which is so this is center mark, or That's all right. So this is your center mark here, which is one stroke before after the 30 mark. If he is 25, he is 30, so it'll be 30.2. So you're going to be 50 minus 30, because this was the 30 mark. The bold mark is the 30 mark. 30.2, which is, it would be 19.8. Good. So 19.8 is this one here. So you know, clear all the drawings again. So 19.8 is your next one. So here's 19.8. Right, they ask us now 1 divided by 19.8, which is 0.05. We're going to the 71 now. We'll go on to 70. So for the 70, you find the center again, which is what we're going to do. You find the center, the bob, the mass. Good. Which is one stroke before this mark here. So it'll be 30, 31, 32, 32.2, 32.4, 32.6, 32.8. So you're going to be 50 minus 32.8. So your whole distance between here to here is actually 1550 minus 32.8, which is actually 17.2 centimeters. Good. Everybody understanding this so far? IGC. IGC students, let me know. Nice. Good. So, moving on to this one here. So it was 17.2 we get here, and 1 divided by 17.2, you get 0.058. So we run it up to 6, yes, 0.06. Then we go down to the 80 mark now. 80 mark is in the center, so here's 30, here's 35 is in the center, then 40. So here here is 35. Right, so here's 35. So you're going to be 50 minus 35. So your answer will be 15. Good. So your fourth one is 15. So you're going down to 15. Good. 1 divided by 15, you get 0.067, or I would just say 7, yes. 0.7. Right, they said for each of the values, calculate 1 over d and record it in the table. No, which we just did. So they said describe one difficulty the student might have when carrying out this experiment and how he might overcome this difficulty. So what is one of the difficulty that he could he would encounter if he tried to balance his beam? So the first thing it would be is difficulty in achieving balance how he could get better and how he might overcome this difficulty. He can overcome this difficulty by How do you think he could overcome this difficulty? We did something similar to this. How do you think? I think he could overcome this balancing problem. Hmm? Anybody have any ideas? Okay. Well, firstly, if it's difficulty and it's about balancing, that means it had to be something obviously going to balance, and you're going to find trouble um, getting it to balance. So he can overcome this difficulty by, firstly, he could do it by finding the average readings, right? Find difficulty by finding the average value taken from both on the left hand, from both on the on both from both sides. Using both sides. So what he could do is that he could take the value on the left hand side and then take it on the right hand side. Like how we have the balancing beam here, the 50, put the weight here, and you take the reading here. You switch around the ruler, you turn around the ruler on the other side, and instead of this on the left hand side, it could be on the right hand side. You take the two readings and find the average value. Alright, so find the average value taken from both sides. So where this is right now, this is on the left hand side. What he could do, he could just turn around the ruler for it to face on the right hand side and take back the same reading. And if it's the same value, whatever value you get, he add the two values together and divide it by 2, and that's what we might take in the average from both sides. Now they're asking us in this question here, plot a graph of M versus against 1 over d. So M on your y-axis and d on your x-axis. So we need to plot this graph here. Your values of M being 40, 50, 60, 70, 80, and 1 over d being 0 0.3, 0 0.4, 0 0.5, and so forth. Good, so we see how best we could. Right, so right, so we're going to draw this graph now. Between this point here, right, so we're going to have M on this side. Shit. We're going to have M on this side and 1 over d on this side. All right, so M, your values was 40, 50, So your first mark would be here. I'm trying to draw it good so that all right. All right, well, I'll just draw it back, yes. So we drawing two graphs. You could draw the two graphs by the time for me. The first one being on the x-axis, which is m. The y-axis, sorry, is m, and on your x-axis is 1 over d. So here, your first line we could label it as 40. Here is 50. What am I doing by? Here should be 40. Here should be 50. Here should be 60. Here should be 70. The top one should be 80. Here should be 0.303. Here should be 0.04, 0.05, 0.06, 0.07. We're going to draw, so you'll get a graph looking like this, something similar to that, a straight line graph. Now remind you, you are not to join it to the 0 point, so your graph will look a straight line like this. Good. Anybody get that so far? My graph not so good on the thing since I had to draw it on the screen. Alright, so we're getting last one somewhere around here. Good. So yeah, so you get 5 points line up on the graph plot. Yeah, so suppose I get something similar to that. Everybody get that so far? IGC students, so I get to plot it like that. All I get to plot it, I want to know so I could move on. People. Nice. Right, so we're moving on. So they ask us to calculate the gradient now. So we're gonna clear all of this so we can move on. Clear all. So we have something similar to that. They ask us to calculate the gradient. You're calculating the gradient using the formula G is equals to M2 minus M1 over 1 over D2 minus 1 over D1. Good. Which is, what is the M2 value? So I am going to assume that our M2 values, we're going to use the big triangle. So your M2 value could be going to be 80 minus 40 over your D2, which would have been 0.07 minus 0.03, one big triangle. So you remember when you draw the straight line, what you could take a triangle anyway. So when I get a triangle, this could be 1 over D1, 1 over D2. Here should be M1, and up here should be M2. Good. So you're going to be 80 minus 40 is 40 divided by 0 0.04. 40 divided by 0 0.04. We get 1,000, so G is around 1,000. That's the gradient. 1,000 is the value so far. Right, and that's all it asks us to calculate G. Anyone get that or close to that at least? If you want, you could have just use the values from the table, which is what I did. What I did from the values from the table here. I just use the top one, which is 40, which is your M, against your 1D1. So you come like use the lowest and the highest value, 80 minus 40, and 0.07 minus 0.03. And you get it. You could work it like that and all because everybody is just going to get a straight line graph for your IGC. Only straight lines. Alright. So we okay with that so far? Nice. Good. So moving forward now. Right. So the question here says now, so we calculate this value to have been 1,000. Right. Determine the mass mu of the load X using the equation. So mu, if mu, right? So if mu is G over 40 and G was what value we calculated to be 1,000. 1,000 divided by 40. 1,000 divided by 40 is we work it in our calculator is how much? 1,000 divided by 40, which is what I get. Anybody? What value will I get? So 1,000 divided by 40 should give it 25 grams. The unit is in grams, this is G. Good, so when you work out that in a calculator, you get 25 grams. Good. So that's question 1. So normally in your paper, for IGC students, in your paper 61, which is your lab paper, you have 3 questions. One on how to carry out an experiment, one on analysis of a lab. Next one is measurement and reading, and the third one is well, justifications, basically just justifying why you get certain results. Good. Oh well, I have the G here already, so we didn't need to put in the G. So it's 25. So you're moving forward. Nice. We're going on to question 2 now. Question 2, here we're saying question 2. Question 2 says a student is investigating the effects of a layer of cotton wool on the cooling of a test tube of water. Figure 2.1 shows the apparatus. So you have some water in the test tube here. This is your test tube. This is your thermometer. This is your hot water. This is your test tube. And this is your stand. They said now record room temperature theta R as shown in the thermometer. It's real poor boy. Alright. Well, the value should have been around 23. I just telling you because they're real difficult to see. So you have to check each increment. So here is 20, here's 21, 22, 23. So it's 23 degrees here. So it's 23 degrees. So theta R is 23 degrees. 23 degrees. They said a student, so a student pours hot water into the test tube until it is about 2/3 full of water. Until the test tube is 2/3 full of water and places the thermometer in the water. She measures the initial temperature of theta of the hot water and immediately starts a stop clock. So as soon as she put in the thermometer, she take the reading and start the stop clock one time. After some time, when she take her next reading. So they said, suggest one precaution that the student takes to make sure that her reading is as accurate as possible. Now we're going back to identify where the fault was, so we're gonna what we should write. He said a student pours hot water into the test tube until it is about 2/3 full of water and places the thermometer in the water. She measures the initial temperature of the hot water and immediately starts the stop clock. Suggest one precaution that the student takes to make sure that her temperature reading is as accurate as possible. What do you think we could do? First, I was giving you some ideas, so let me guess. Number one. One of your answers should have been take reading of thermometer. Take reading of thermometer when level stop rising. When fluid level stop rising. So the mercury in the thermometer, as soon as that stop, that's the time you're going to take the reading. The second one, you take the reading at eye level. Take reading at eye level. This is to prevent something called parallax error. Alright? So take reading at eye level. And the third one, I'm giving you a third one here, which is a third answer. You could learn how much you want. A third one is to stir water so that the temperature is even throughout the liquid. Okay, so the water might be hot, but certain points in the water it might be degrees off because parts of the water might be hot and then other parts might be cool. So you stir it up to make sure the temperature distributed evenly. Good. So that is one of the reasons in order to get a more accurate reading. So those are three reasons. They only asked for one though. So they said now the student records in table 2 the time t and the temperature theta of the water every 30 seconds. So it's every 30 seconds. So she started at 0. So she removes the thermometer and pours away the water from the test tube. She then wraps cotton wool insulation around the test tube and repeats the procedure. Complete the time column and the column headings of table 2.1. So time is given in seconds, and your temperature is given in degrees. Yeah. All right. So temperature is given in degrees. So the first is started off at 0, then 30. After 30 seconds is another 30 seconds again. 30 plus 30 is 60. You're going to add an next 30 again. 60 plus 30 is 90. You're going to add an next 30 again, 30 seconds, which is 90 plus 30 is 120. Add an next 30 going to be 150. Add an next 30 going to be 180. Good. So those are the values that would have had in the experiment. So you started off at time 0. After 0 is every 30 seconds and you take a reading. So at time 0 the temperature was 79 without the cotton wool and 80 with the cotton wool. and you gradually decrease as it goes on, as it takes longer. Write a conclusion. Now they said, write a conclusion to this investigation stating in which experiment the cooling is more rapid. Explain your answer by reference to the readings on any relevant science. Good. So write a conclusion on the investigation. So let us pay attention to, before writing the investigation, what we could analyze out of this whole experiment. So because one of your questions is an analysis, right? So 0 to 30, when the temperature now started with and without the cotton wool, the temperatures was close temperature. Then as time go by, the last reading, the temperatures was still close. Here we go, we take a random one. At 120, yeah, temperatures was still close. There's some degrees of 2-3 degrees. So they are asking now, write a conclusion to the investigation stating in which experiment the cooling is more rapid. Explain your answer by reference to the reading or any relevant science. So without the cotton cloth, you are just 1 degree off or 2 degree off from the previous reading. With the cotton cloth is 1 degree or 2 degree off. So the cotton cloth really do play a particular role in this whole experiment, because without the cotton wool, you are still going to get close readings. But with the cotton wool, you just get 1 slightly off reading, like one or 2 degrees slightly off. So we could justify this by saying, explain in your answer, write a conclusion to the investigation stating in which experiment the cooling is more rapid. So from the investigation, write a conclusion. We can see that the cooling is rapid for both experiment. Values were very similar, was slightly different, which means was slightly different. This meant that the cotton wool is not a good thermal insulator. Right? Is not a good thermal insulator. So that means it doesn't keep the heat. So the cotton wool really do play a particular role in this whole thing. It is not a good thermal. A good thermal insulator is something like Cyratex, which means that when you boil the water in a Cyratex cup, you are not going to get burned, but the temperature going to stay at its value until you stir it or throw it away or do whatever. Right? So those are the answers, and we can see that the cooling is rapid in both experiments. Values were slightly different. This meant that the cotton wool is not a good thermal insulator. Good. Which is the 3 points we're really looking for here. All right. So everybody okay with that? IGC students, you all okay with that so far? Are you okay with that? Need to message me so I have an idea. All right. Right, the question here says, discuss the quality of the results. Suggest 2 improvements of the experiment which would allow a certain conclusion to be drawn. So what is the quality of the results? What we just talked about, there's a slight temperature change in difference. So the quality of results is 4 due to due to due to due to the small temperature difference existing differences. Good. And how are we going to improve this? Well, the first one, we could improve it in a number of ways. How we could improve this experiment to be much accurate is to increase the initial temperature of hot water. So instead of the hot water being 80 degrees, let me carry it up to 90 or 100 degrees. The first thing. Or so in that way we'll get a wider range of readings. We could get one at 0, and we could smallen the time as well or increase the time. We could also use a lid to cover test tube. Why we want to use a lid to cover the test tube? So that the temperature would be only confined to the test tube itself. So as a second reading, a second way to improve it, and a third way, you could stir water to ensure that the temperature of water is stir water to eliminate the temperature differences. Alright, so those are some 3 ideas. They only ask for just to say the 2 improvements, however given it 3. So just in case this question come back, you should be able to. So study water to eliminate temperature difference, because we had made mention of that far earlier. Everybody okay with these answers so far? Okay. The question here says in F now. In F of the question, this says the experiment is being carried out by students in different countries using the same or the identical apparatus. Suggest 2 differences in the conditions in the various laboratories that might lead to differences in their results. Firstly, different countries mean that the room temperature is going to be different. So that means your laboratory temperature is going to be different. So state 2 differences. The laboratory temperature is going to be different because the room temperature is going to be different, because the temperature in countries vary. And the second one could be the design of laboratory um, in design of laboratory allowing for open windows, right? Which means that some labs are more closed up than others, and if the lab aren't designed the same way, then obviously the lab temperature is going to be different. And even if the lab temperature not different, because the windows are always open and so forth, you're going to have a variation in the laboratory temperatures. Good. Estimate the volume. Everybody okay with that? You could also say that the temperature of the hot water. Everybody might use different temperature of hot water. I'll put that to one for you. So number three, you could also say that um different 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 um different temperatures of hot water use. All right. So that's a third one because the same apparatus, just they might not start at 80 degrees, they might start at 100 or 90 or 75 or whatever it be. All right. They said in G, estimate estimate the volume of water that a test tube can hold. Estimate the volume of water that a test tube can hold. A test tube could hold about an average of 50 cm cube. Alright, that was 50 cm cube of water they could hold a standard test tube. Alright, everybody okay with question 2 so far? IGCSE students. Nice. Is it possible we could take a break from now till half 6, take a 15 minutes break, and we'll come back to the question 3 and question 4. So we'll take a break now, and we will resume at 6:30 p.m. Alright, well, welcome again. So we continue now with question 3 from our paper here. So question 3 in the past paper, the specimen paper, we are saying here, it says a student is investigating the effects of the length of resistance wire in a circuit on the potential difference across the lamp. So what happened is this here, in this circuit here, when I close the switch, current flow through. When you adjust the movement between points A to B, the lamp would either become bright, dull, or off. Good. It's a complete diagram to show a voltmeter connected. So they ask if a voltmeter here connected to the circuit to measure the potential difference across the lamp. So if you had a draw voltmeter, a symbol for voltmeter is a circuit with a V-net, and it must be connected in parallel across the component. Good. So this is how it's supposed to be drawn. No, neater than that though. Good. So must be across the bulb. So that's how we draw the voltmeter. The keyword is voltmeter. Voltmeter means it must be drawn in parallel. Good. To measure the potential difference across the lamp. So we okay with that thus far? So far we okay with that? Class? Right, nice. Moving on. They said here now, lower down, they said the student switches on and places the sliding contact C on the resistance wire at a distance L is equal to 0.2 meters from end A. So here is 0.2 meters, which is 0.2 meters. Good. That's the whole length there. Lower down they said now the voltmeter reading is shown here. So they ask here To complete this table, they said record the voltmeter reading in table 3.1. So we're going to check the value here of the the, the voltmeter. So here's 1 and 0 and here's 1. Between here we have 1, 2, 3, 4, 5. So each of these is going to be a stroke. So here going to be 0 0.2. Here going to be 0 0.4. Here going to be 0 0.6. Here going to be 0 0.8. Here going to be 1.2, 1.4, 1.6. Here going to be 1.8. So if here is 1.6, then this means this stroke here going to be 1.7. So the stroke before, so it will be 1.6, 1.62, 1.64, 1.66, 1.68. So answer should be 1.68 here. Again, so 1.68 should be answer for this part of the table. 1.68. Again, so it's 1.68. So at 2 you get 1.68, at 4 you get 1.43, at 6 you get 1.25, at 8 you get 1.11, and at 1 you get 1. So the student repeats the procedure using a range of values L shown in table 3.1 shows the reading. Use the results for the potential difference across the lamp to predict how the length affects the brightness of the lamp. So the voltage now, what's the voltage? This is the voltage here. Here's the voltage. Here's the voltage across the lamp. So here at this point, you're going to light the brightest. Light the brightest. Here, you're going to be dull. So, if you notice, as the length increase, your voltage going to decrease. So your voltage decrease here. So L is directly proportional to V. So when L increase, your V decreases. So they said here in the question, state the student repeats the procedure using a range of values of L. Show the readings. Use the results of the potential difference across the lamp to predict how the increase in length affects the brightness of the lamp. So exactly what we see here. As the length increases, so as the length here, as the length increases, increases, as the length increases, comma, the voltage decreases, which means this means this means that as the length increases, as the length increases, as the length increases, the bulb, the brightness of the bulb decreases. Good? Because why? When L increase, your V decreases, or vice versa. So that means that, oh, all right. The brightness of the lamp decreases, right? Right. So that's what we mean by that. Because the voltage drop. When the voltage drops, the lamp itself going to have less power, so the lamp will be lightened, dull. Good. So we're moving down now. Part D of the question. They say the students suggest that the potential difference across the lamp is directly proportional to the length of the resistance of the wire. State whether you you agree with this suggestion. No, we just show it. You agree with this? No. Your answer should be no because should be no. Why? Because what we notice here, we notice that when your length increases, that your L is directly proportional to your voltage, which means that it's indirectly proportional. Because only when your length increase, your V decreases. It's good. So it means that here that the length is um voltage. The voltage is inversely proportional the length. The greater the length, the greater the resistance, the greater the resistance in wire, the greater the resistance in the wire, the greater the voltage drop. In the wire, lesser lesser the voltage, lesser the voltage, lesser the voltage across bulb, across lamp, or hence which is equals lamp lights, brightness of lamp decreases. Good. The voltage is inversely proportional to the length, which means that the greater the length, the greater the resistance in the wire, the greater the voltage drop in the wire, lesser the voltage across the lamp, and the brightness of lamp decreases. Now, all of those is in layman terms. I just put equal sign to show you what's going to happen next. Good. So everybody okay with that so far? Nice. We're moving on. They said now the student repeats the experiment. Suggest a practical reason why the repeat readings might be slightly different from those recorded. So you do back the same experiment, but you get slightly different readings. The first thing could cause that is the resistance wire. Right? So the first one could be achieving the same position on the rheostat, or the resistance wire, we're gonna call it. Right? Achieving the same position. He might not be able to achieve the same position, which means it wouldn't be the same distance along the wire. Right? So that's the first one. The second point you could come up with is that temperature changes temperature changes affects the resistance value resistance values. Again, so those are two. Due to something called temperature coefficient of resistance, increase in temperature can also cause an increase in resistance. Or another way, an increase in temperature could cause a decrease in resistance. So it based on temperature changes could affect the resistance value. So those are two. They only ask for one, however, I give you two, so in case for future wise. State one safety precaution that you would take when carrying out experiment like this with resistance wires. So you're dealing with resistance wires. First thing, to do not touch the hot wire with your hands. Alright, so do not touch hot wire with your bare hands. And then two, the second one is do not connect terminals of the resistance wire to the directly to the battery terminals. Alright, directly to the battery terminals. Why? What can happen is if you connect it directly to it, it could become hot and it could burn you. Then, so two examples. You only ask for one, so I just give you a second one. Alright, so those are two.